Okay, so that wraps up for one-way ANOVA. So let me just briefly mention some of the, well, actually, maybe I'll just dig back into a couple more topics with one-way ANOVA. Okay, so here our p-value is around 0.001. And so I'll just write maybe the proper interpretation of our p-value, etc., etc., etc. Okay? And then we'll just talk a little bit more about ANOVA, and then we'll start a little bit of a review. Okay. So recall, I just erased it, but we were talking about the age at which smoking began, and we said the null hypothesis can be that the means of the three groups are equal, or we could also write it as someone could rephrase it as the effect of being in a group so these are essentially saying the same thing, or at least for one-way ANOVA. And the alternative would be that at least one mean is different. And the alternative here would be that at least one group effect is not zero. So we say the effect of being in one ethnic group has no effect, or it does have an effect. And we found the p-value to be was around 0.001. Okay. So what this says is that if we assume that the null hypothesis is true, meaning that all three groups have the same mean, the probability that randomly selected data give us, means that are different, that are as different as 17.3, 17.5, and 18.4, that probability is around 0.001. Okay. So it is unlikely that we saw our data because of random chance alone. So we reject the null hypothesis and conclude that ethnicity tells a lie. just like all the other tests, when your p-value is small, you reject the null hypothesis and conclude that we have evidence to support the alternative hypothesis. Yes.
What if the p-value for the test statistic was closer to the middle between those two numbers? Like it was 7.5, which is pretty close to 7.26, which is why we're saying it's around 0.0.
Yeah, you know, yeah, I would probably say the p-value is less than 0.001 and greater than 0.0001. Okay, which is what I would recommend you do for, in general. Okay. Just like for the chi-squared table and all the other tables that you have to use, t-tables. Same usage. Okay, let me just briefly mention other forms of ANOVA that you might come across. Okay, so we have what we call a randomized block design. Randomized block design, and in this case, there are essentially two factors, okay? So, two factors, but we're only interested in one, okay? Only really interested in one. I don't know. Interested in one. Okay. So we have the factor, and then the other one, we want to account for it in our analysis, and that is our block. So, for example, let's say you wanted to do an experiment on some mice, okay? And you got a bunch of mice, and let's say you're curious what the effect that some drug has on mice, okay? So we want to know the effect of a drug on mice. So maybe we have, drug A, drug B, and placebo or control. I guess with mice you don't really need a placebo. It's not like, I don't think there's a placebo effect on mice, but maybe there is, who knows. Okay. But let's say, I don't know. You have trouble finding mice, and so, or actually, your sources of mice, there's, I don't know, two places where you get mice from, okay? And you needed to get like a bunch of mice, but you couldn't, there wasn't enough to get them all from one place. Okay, so you're going to get mice from, I don't know, company A and mice from company B. Is there a mouse factory somewhere? Who knows? I don't know where the mice come from, okay? Huh? Yeah. So, yeah, that's a good question. I have no idea where mice are bred for lab experiments. Creatures. Okay, poor things. All right. So we have mice from company A, or we'll call them company X, and mice from company Y. And let's just say, historically you've known that the mice you get from company X are different from the mice from company Y. We don't know what they're doing at these companies or what's different, but we just know that, overall, it seems like the mice are a little bit different, okay? Well, traditionally in an experiment, you randomly assign the treatments to the subjects, okay? But if you did random assignment in this case, from random assignment, it's very possible that drug A gets assigned mostly to mice from company X. And it's also possible that drug B gets assigned mostly to mice from company Y. And maybe we get a mix in both or something. And let's say at the end of the experiment, we see that these mice, I don't know, showed better results than these mice. Okay? That the drug A mice showed better results than the drug B mice. Okay? Well, if most of the mice that received drug A were from company X, and most of the mice that received drug B were from company Y, at the end of the experiment, we might not be sure if the positive results of drug A, or the positive results that we see in this group, was because drug A was more effective, or if the mice from company X just performed better. Okay? So in that case, we have an issue of what we call confounded variables. We don't know, so, let's just, for simplicity, let's just say these were all ended up from company X, and over here it was company Y. Here we have a mix, okay? Well, if we see this one had, great improvement, and over here we had little improvement, and here we had, mixed results. We don't know if the great improvement is because of drug A, or if it's because of the difference in mice. Okay. This is the result of the drug. Or the different mice suppliers. Okay. And and this problem exists for lots of things, and this is the very reason why you cannot just have one subject in a treatment group. Okay? If you assign a treatment to just one person or one subject, you don't know if the results that you see is a result of that individual or the treatment. Okay? And likewise, if everybody assigned to drug A is similar or has something in common, such as coming from company X or whatever else it might be, you won't know if the results at the end are attributed to the different treatment or this other thing. Okay. So in this case, we want to set up a randomized block design so we can kind of isolate the effect of the drugs. Okay? So we have mice from company X and mice from company Y. In a randomized block design, what we want to do is we want to make sure that the mice from company X are assigned to all three groups, the mice from company Y are assigned to all three groups, or that within each treatment we have mice from both companies. Okay, so we want to make sure we have, let's say 5 from X, 5 from Y. Okay, and so on and so forth. Okay, 5X, 5Y, 5X, and 5Y. Okay. So we want to make sure that we have both groups, X and Y, represented in the different treatments. And then in the analysis, if we see overall that drug A performed better than drug B, then we know it's because the drugs were better, or the drug was more effective than, and not just because the mice from the different companies are different. So in a randomized block design, assign members of each block to the different treatments. And you just have a few questions in your homework dealing with this concept of randomizing and blocking. Yes?
So in your definition, you said there's 2 factors and we're only interested in one?
Okay, so we have one factor and we have one block. I guess I'm a little sloppy in my wording here. But in this case, we're just interested in the effect of the drug. We're not really interested in the difference between the two mice companies. And that's a silly example with the mice, but it often plays a role if you're doing experiments. And a lot of times you can only do so many experiments in a day. Okay, so you have to do different conditions of the experiment in batches. Okay, and so you want to kind of make sure that you get a good mix in each batch, and not just do them sequentially, because you might find that the earlier batches look one way, the later batches look another way, and you don't know if it's because the different setups or just the different times play a role. So that's randomized block design. In a randomized block design, so now I'm going to use the alternate formulation. We say in a randomized block design, each value y is due to, comes from the grand mean, plus treatment effect the effect of being in a block plus any individual difference. Okay, and of course any treatment or block effect or individual difference could be positive or negative. And so your hypotheses here, essentially you would do a few hypotheses. You'd have two hypothesis tests. One is you're seeing if the different taus are equal to 0, and then the other one is you're seeing if the blocks are equal to 0. The effect of being in the block. Are those equal to 0? Okay, but not to worry, you won't actually have to do this. But I'm just letting you know that this exists, okay? Actually, if you're going to take more statistics classes, I think a design of experiments analysis of variance is a good class to kind of get your feet a little bit deeper into the subject matter. So you can see all sorts of this stuff. Yeah?
So if you end up with like, if you try to do it randomly and you end up with a lot of, say, mice from company X in one drug and another from company Y in the other drug, is there a accepted method, like, do you just randomize and do it again, or do you try to
Yeah, you would,
put it in a certain way?
you would say I'm going to randomly select 5 mice from X to assign to drug A, and randomly assign 5 mice from Y to assign to drug A. So that's the randomized block design. So you're keeping kind of the counts of the blocks in mind when you're doing your random selection. And you're not just saying, here's all my mice, let's randomly assign them all. Because then you can end up with those oddities. And you definitely don't want to just say, okay, here's my first 10 mice from A, we're going into drug A. Yes?
I might have missed this, but why did you choose 5? Another
Arbitrary.
Okay.
Yeah, not. Because I wanted to put in some number there. That was, but I just made that up. Okay. Okay, so that is randomized block design. Okay, then we have two-way ANOVA. Okay. And in two-way ANOVA, we have 2 factors, and we're interested in both. And there might be an interaction between the 2. Okay, so we have 2 factors, interested in both. And maybe there is an interaction, a possible interaction between the factors. Okay, so maybe, this is a terrible example, but I don't know, let's say we were interested in how long someone can run before they need to take a break or something, okay? So, you know, we get a bunch of different people, and we want to know how long can you go running full, you know, at top speed before you need to take a break or something. And we're going to try this experiment in different sets of conditions, okay? One is we're going to simulate high altitude or low air pressure or something, okay? So maybe we'll put you in a room with where the oxygen is thinner, versus control, okay? And maybe the other thing we're interested in is we're interested in whether people who have asthma are affected in terms of how far they can run, okay? And so what we would expect to see is that, you know, in the lower, less oxygen situation, people will be able to run less. And then we would also expect to see people who have asthma would not be able to run as far either, okay? But what we also might see is an interaction between the asthma and the oxygen level, in that maybe lower oxygen generally decreases someone's performance by, I don't know, let's say 5 minutes running or something, okay? They can't run. And then maybe having asthma reduces someone's ability to run by, I don't know, another 5 minutes, okay? What we might see is that rather than just an added 5 plus 5, when we stick people with asthma into the low oxygen environment, rather than seeing a 10-minute reduction, we might see something like a 20-minute reduction, or an even greater reduction, because maybe the low oxygen affects people with asthma to an even greater extent otherwise, okay? And so with two-way ANOVA, you would find the effect due to each of those individual factors by themselves, and you might also find an effect between the two factors interacting with each other, okay? And so two-way ANOVA would allow you to pick up on that. And the formulation there is that y is equal to mu plus treatment effect. Oh, how did they? Oh, I guess the book uses tau and beta still, and then they stick in gamma for the interaction. So this is treatment 1, or factor 1, I should say. Factor 1, factor 2, and then the interaction. And then you would have 3 hypotheses. Is factor 1, are the different factor 1s equal to 0? Or is there a difference between factor 2? Is there a difference in the interactions? Okay, again, don't worry about this. But that's what we got. Okay? Alright, so that's all I've got for ANOVA. And I guess it took a little longer than I thought. We'll spend some time in review. Is that okay? Alright. So next week, we're covering chapter 12, which is all on regression and correlation and all that stuff, okay? Okay, so on part of the test, or an important thing in statistics is, you know, when you're faced with a situation, you've got to know what is the appropriate statistical method or statistical test to apply in this case. So I have a section where on the final exam, where I describe a scenario and the data that's being collected, and you have to say, in this case, we should use this test, or in this case, we should use this test. Okay, so how do we know which test to use? And I do have a little guide on the class website. I just want to kind of want to make sure that what I put on the board here looks like the guide that I posted. Okay, so what we're going to look at is, our first question is do we have a numeric response or a categorical response? Numeric on top. So we might have the response being numeric, or it could be categorical. Right? Then we look at our predictor. Okay? So if we have a numeric response and a numeric predictor, then in this case we will use the one thing that we haven't learned, which is correlation and regression. Okay. So if your response is numeric and your predictor is numeric, we would use correlation, regression, and we also have, and in that chapter we'll learn a test for significant correlation. Okay. So we haven't learned that yet, we will learn that next week. And that will, I will repeatedly say you need two numeric variables, the numeric response and the numeric predictor. Alright, if we have a numeric response and a categorical predictor, then we have all kinds of situations. Let me just make sure I'm following the same guide here. Okay. So with a categorical predictor, we can have two groups only, or more than two groups. So if you have a categorical predictor, numeric response, and more than two groups, this is what we learned today, use ANOVA. So if you have more than two groups, have to use ANOVA. You could use ANOVA for only two groups, but it seems unnecessary. Okay. Okay. Then when we have two groups, we want to see if the two groups are independent of each other, or if there's a relationship between the two groups. Independent or paired. If the two groups are paired, well, I only taught you how to deal with one paired situation, okay? And in that case I said use the paired t-test. If our two groups are independent, we have two situations to use. We have the regular old t-test, okay? And then we have the Wilcoxon-Mann-Whitney test. Okay, is it alright that I'm just abbreviating Wilcoxon-Mann-Whitney? Is this? When would we use the regular old t-test, and when would we use When do we use the Wilcoxon-Mann-Whitney test? So the t-test assumes normal distribution, okay? So that means, it doesn't mean the parent population has to be normal. It just means the central limit theorem has to hold. So you either need large samples, or if you have a small sample, no outliers. Okay? So t-test, you either have large sample, and then it doesn't matter if your parent population is normal or not, or no outliers. Okay. With a Wilcoxon-Mann-Whitney test, if you have outliers and it's a small sample, then you would use the Wilcoxon-Mann-Whitney test. So we haven't learned correlation regression yet, but I don't think it's too hard to say. If you have a numeric response and a numeric predictor, that's what you're going to use. So all these other weeks we've done all of this stuff here. Okay. All right, categorical response. Let me just make sure. All of this. Okay, with the categorical response, we might have no predictors. Okay. If we have no predictors, then what kind of test are we going to be doing?
Chi-square?
Yeah, okay, so chi-square test, but there's two tests, chi-square tests that you learn. Chi-square test for goodness of fit and chi-square test for independence. So if we have no predictors, we would do the chi-square goodness of fit test. Okay. Chi-square goodness of fit means we have some proportions in mind, and we want to see if that fits our response variable. So this is the one where we have proportions in mind. No predictors. You could also do confidence interval for P, okay, using P tilde. And that is if we have only two categories. Or basically, it's just the proportion of this versus the proportion that's not. On the other hand, for a categorical response, we only covered the case for a categorical predictor. And in that case, we would do the chi-square test for independence. Combination that is not up here, and we will not learn in this class, would be categorical response numeric predictor, and that is called logistic regression. We will not be learning that. Okay. So when you're faced with something, follow this tree diagram and use the appropriate test, okay? You have to be careful. Sometimes a variable, the same variable can be treated as categorical or numeric. Okay? So a simple example would be if we say someone's age. Normally we would think that as a numeric variable, whether they, just their age in years. We say someone is 32, we treat that as a numeric variable. But, when it comes to law, rarely does the number actually matter. It's the category. Are you an adult or are you a minor? Okay, so we've taken what is normally seen as a numeric variable, but we've turned it into a category. Adult versus minor. Okay? Generally, those are the only two categories that matter in legal circumstances. And so in those cases, okay, and so when you look at your data, you have to ask, is my data being recorded numerically or is it being recorded categorically? Okay? We could ask, is there a relationship between numeric response, number of time spent online, is that connected to someone's age? Okay. So if we treated time spent online versus someone's age as a numeric predictor, then we would use correlation regression. If we treat age as minor versus adult, or if we have different demographic categories and say you're in the under 25 group, you're in the 25 to 40 group, and you're in the, whatever demographic categories you have, then that would be a categorical predictor. Okay, so you have to read carefully as to whether the data is collected as a numeric variable or a categorical variable. Is that okay? Yes?
So the predictor is the data is given in that format, the results.
So usually you have a response variable and what we call a predictor variable. So yeah, whether it's numeric or categorical depends on how it's being recorded. Okay. Obviously, if there's just a hint, if there's units involved, it's going to be numeric. Okay. If it's being measured in years, that's a numeric. If it's being measured in pounds, that's going to be a numeric variable. Okay. You're not going to have a categorical variable measured in pounds. And I'm trying to think of a situation where that might be possible. And no. Okay. We might categorize people based on their weight. So, for example, in competitive boxing, they're categorized in weight categories. Featherweight, lightweight, heavyweight, all of these, welterweight, all of these different weight categories. Okay, so they take a numeric variable, how much someone weighs, and then they say, oh, if you weigh this much, you're put in this class. Okay, and so, but in that case, their weight class is not recorded in pounds, it's recorded as this category name. Okay. So just be on the lookout for that. Okay, so you'll need to be familiar with which tests to use. Here, we can try a few examples here. And the end of chapter 13 is like a review chapter in the book itself. And there's an even more complicated version of this table that shows you all the other tests that we did not cover in this class. But let's see. I hurt my hand earlier today. Page. Where did it go? Page 563. Okay. So I will read this to you guys. If you have your book, you can turn to page 563 and follow along. But I'm going to read this out loud, and you tell me which test is appropriate. Okay? Don't shout it out, just so other people can think of the answer. So don't shout out your answer, but think which statistical test should be used. It says, researchers conducted a randomized, double-blind clinical trial in which some patients with schizophrenia were given the drug clozapine, am I pronouncing that right?
Mm-hmm.
And others were given haloperidol. Clozapine and haloperidol. After 1 year, 61 out of the 163 patients in the clozapine group showed clinically important improvement in symptoms.